All right, here we go. Here's another exciting day, another exciting episode of Advanced Level Chemistry here. Today is Tuesday, December the 9th. Okay? Wow, time flies. We're getting close to Christmas. Okay? All right, so what are they supposed to do if they're liking these videos?
Smash the subscribe button.
You ring that notification bell. Ding, ding. All right. Okay, so let's look at these. Make sure we know. Again, if there's something that you're just unsure about, this is the time to ask the question. We've got to make sure we can draw these Lewis dot structures. So again, what's the very most important first step?
Find the number of electrons.
Number of electrons. So we have 7 times 3 is 21, plus 5 is 26 electrons. What's the central atom going to be?
P.
Why?
Because there's only one.
It's the least one, okay? So phosphorus is going to be the central, and then we draw single bonds building around the phosphorus. 2, 4, 6. Now, where do I start adding electrons? In the middle or at the outside? Outside. Always in pairs. You're never going to do one at a time, but electrons always hang out in pairs like girls go in the bathroom. So it's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So where do extra electrons go? Central atom always. We don't need to form any double bonds or anything. We just put it there. Everything's got its 8. If it ain't broke, don't fix it. Okay? So what's my AX formula going to be for this? AX3E. So the shape is going to be trigonal pyramidal. Now, if you want to sound really fancy, if you want to sound really educated, okay, you can say pyramidal. Pyramidal instead of pyramidal. Pyramidal. Okay? You put your emphasis on a different syllabus. Okay? You put your emphasis on a different syllabus.
Bro, emphasis on a different syllable.
Yeah. All right. VRF5. 6 times 7 is 42 electrons. Okay? So, bromine, 1, 2, 3, 4, 5. Okay? Back row. Okay? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Where do extra electrons go?
Central atom.
Central atom. Okay, again, find a spot in between. This is the biggest spot, so I'm going to put it right there. So again, now how many electron pairs are around the bromine? 6. 5 bonding and 1 lone pair. Okay? What do we call it when there's more than 4 pair or more than 8 electrons around it?
Extended octet.
Not extended, an expanded octet. So this, and only remember, only elements on the group 3 and below. In other words, carbon, nitrogen, oxygen, fluorine, neon, those are all too small to have an expanded octet, but everything else can.
We should probably turn it back.
Okay? So what's my AX formula here?
AX5E.
AX5E, so the shape, you just look on your sheet, square, pyramidal. Pyramidal.
I said it over.
Okay? So then we go over to the next one. 12, 17, 18 electrons. Chlorine is going to be the central atom because hydrogen is never the central atom. Hydrogen is always peripheral. Okay? Put your oxygen, oxygen. Now where does the hydrogen go? On the chlorine or the oxygen?
Oxygen.
Always on the oxygen. Okay? Pick either one. I'm going to go here since there's a hole there. I'm going to use that as a lone pair. Okay? And it's going to end up looking like that. Okay? Now, we have 2 central atoms here. But they're both, what AX formula?
AX2E2.
AX2E2, so they're both going to be what shape?
Bent.
Bent. Okay, so you always say the shape around each central atom. You don't have an overall shape of the molecule. And then lastly, nitrogen. What does the minus mean? Okay, because it's an ion, that means it's got one extra electron. Ions are made by gaining or losing electrons, oxidation and reduction. Okay, and so we have one extra. So how many electrons total does this have?
25.
Try again. 24. 24. Here we go. 24 electrons. 24. So it's nitrogen, oxygen, oxygen, oxygen. 2, 4, 6. 8, 10, 12, 14, 16, 18, 20, 22, 24. So what's the issue here? Nitrogen doesn't have enough. Okay? Now we can't just add more, so what do we have to do? Form a double bond. Doesn't matter which one. No, we're going to come back. Y'all listen, there's a lot of extraneous talk going on here. Okay? But we're going to learn that this is a special case, but that's going to be something we're going to talk about after Christmas. Okay? On what happens when you have, it could, the double bond could be here, the double bond could have been there, the double bond could have been here. Now because it's an ion, what do I need to do with it? Put it in a bracket with the charge on the outside. Okay? Put it in brackets with the charge on the outside. That just tells me the negative charge is evenly distributed on the whole thing. It's not on one particular oxygen. Okay? Can we do this?
Yes.
Any questions at all about this? You, again, for the bazillionth time, you will have the AX, you will have this sheet on the test. Okay? You just need to know how to use it. Okay? You have this sheet on the test. Did you get one of these? You got to have this. Was anybody else not here yesterday? Okay. Now, the second thing that we have to do is, because y'all freak out that we don't have every blank filled in, get your notes out. Y'all, I appreciate the energy today, but we've got to get some focus. Nothing changed when I said that.
There needs to be a change.
I don't think so. I mean, she's planning on not doing it next year. But I don't know. Yeah.
Okay, this is starting on letter H. I think it's like page 6 overall, page 4 of your covalent bonding notes. No, it's on page 4 or 6. Okay? We already know everything that's going to go in the blanks. Okay? But I'm just going to fill them in just because y'all, I'm trying to relieve stress. The valence shell electron pair repulsion theory says that the valence shell electron pairs, the ones involved in bonding and the lone pairs, the bonding pairs and lone pairs, are going to repel one another. Okay? The electron pairs repel each other. Therefore, molecules adjust their shapes so that the valence electron pairs are as far apart as possible. Okay? That's where all of our shapes come from. That's on our AX formula. This is all about the AX. Since most molecules have 8 electrons, that's your octet, the electrons will arrange themselves in a tetrahedral shape. Okay? Most of them are going to be like that. Okay? Lone pair electrons are still going to affect the shape. Okay? But we only play dot to dot with the nuclei. We already talked about that. So, possible shapes of molecules with all single bonds, 8 electrons around the central atom. Now, this hybridization stuff, we're going to talk about that after Christmas. Okay? It's going to be just a quick little discussion about this hybridization. Okay? But if all 4 pairs are bonding pairs, You got 4 pair of electrons that are all bonding. What's my AX formula going to be? AX4. So in other words, we're talking about AX4 here. So what's the shape going to be? Shape is tetrahedron with what bond angle? 109.5 all the way around. Okay? But if there are 3 bonding pairs and 1 lone pair, what's the AX formula going to be?
AX3E.
So in other words, this one's talking about AX3E. Okay, so we've already talked about it. What's the shape going to be? Trigonal pyramidal. Pyramidal. Okay? But what's the bond angle going to be? About what?
107.
Around 107. Why?
There's closer together.
Because lone pair
Makes them
occupy a greater space. Okay, it's around about 107. Because lone pair occupy a greater space than bonding pairs. There's more electron-electron pulses, which cause the bonding pairs, the bond angles, to be decreased by about 2 to 3 degrees per lone pair. Okay? So I told you everything was in the notes, that everything we talked about yesterday, but we're just filling it in. Now, everybody got that? This is just putting into words everything that's on the sheet from yesterday. Okay? No, that is where I want to be. Now, well, that's what we did. Here we go. If there are 2 bonding pair and 2 lone pair, what's the AX formula? AX2E2. So what's the shape going to be? Bent with a bond angle of about 105. Now it's going to be different for every atom. You're not going to have to know the exact bond angles. You just need to know it's going to be slightly less than 109.5. Okay. Let's turn the page. Okay? If there's 2 single bonds and 1 double bond and 0 lone pair, okay? 2 single bonds and 1 double bond, what's my AX formula going to be?
AX3.
2 single bonds, 1 double bond. AX3. 3 bonds still. What's the shape going to be? Trigonal? Planar. What does planar mean? Flat. Okay? And your bond angle is 120. That's going to be this. Okay? Your 120, 120, 120, all on the inside. The interior angles of a triangle are 120. They add up to 360, a circle. You take geometry so you can apply it to a real subject. Okay? If there's a single bond, a double bond, and a lone pair, what? AX2E. So what's the shape going to be? Bent. Okay? And you're going to have a little bit less bond angle. And then lastly, if it's a triple bond and a single bond, or 2 double bonds, what's my AX formula going to be? A triple bond and a single bond is how many bonds total? How many things bonded to it? There's 4 bonds, but how many things are going to be bonded? If it's a single bond and a triple bond. What's my AX formula? AX2, right? Or if it's 2 double bonds. Okay, it's AX2. Okay? Then it's going to be a linear shape with a bond angle of 180 degrees. Okay, so again, this is just putting into words what's already on the sheet. All right, lastly, before we move on. These are my exceptions to the octet rule, okay? If the central atom contains only 3 pairs of electrons, the shape is trigonoplanar, and don't worry, we'll come back to that. Now, that's old school name, group 3A. That's how long ago I made these notes, okay? It was before 1995. Okay, yeah, a long time ago, okay? What's group 3A's number now? 13. Okay, so we're going to really call this group 13. Boron, aluminum, and gallium. You must know these. This is an exception to the octet rule. Well, it says that. The central atom usually goes through these. Okay? Exception to the octet rule. Now, we're not going to worry about that one. That's group 2. Normally group 2 is going to form ionic bonds. We're not going to worry. We're not going to call this covalent bonds, so don't worry about that. Okay? So this is the exception. You just somehow or other, boron, aluminum, gallium, those show up. You just have to know they only need 6 electrons, not 8. That's just the one exception here. All right, so that's kind of the Vesper theory. Now, we have to learn the shape, because the shape is going to determine a lot of the properties of the compound. I've said before, if water was linear instead of being bent, it would not be a liquid at room temperature, it would be a gas at room temperature, and as a result, life as we know it on Earth would not exist. The shape of the molecule is very important, because it determines the properties of the molecule. One of the most important properties is it polar or nonpolar? We've heard in biology that water is polar. Does anybody remember what that meant? Opposite, what do you mean opposite poles? Say that again. Opposite charge. It's got a positive and negative end. Ions are either positive or negative, but sometimes a molecule can have a positive or a negative end. Okay? And so we're going to talk about these polar bonds and nonpolar bonds. Okay? Well, what's the key word with electrons in a covalent bond? What do they do with electrons in covalent bonds? They share. But if you know, then sometimes in a sharing relationship, the sharing isn't always equal. Okay? If we can have equal sharing, then we're going to have a nonpolar bond. There's this thing called electronegativity. So right here off to the side somewhere, you need to define this term. This is another important term. Electronegativity, an atom's attraction for a shared pair of electrons. So if I look at chlorine, in the Cl2 molecule, the bond, I'm going to let you finish copying. Thank you, Tom. Big word. Electronegativity. Okay? Discovered by Linus Pauling. There's an article in your book. By the way, this is all chapter 12 in your textbook. It's unit 6 in the notes from the old textbook, but it's chapter 12 in your book if you want to go and read. And your book, remember, has all the digital stuff if you want to kind of use it to study from. Okay, so I recommend that maybe you can kind of look at some of that. But what this is this pair of electrons is attracted to the nucleus of that chlorine and the nucleus of that chlorine. It's a tug of war for the electrons. But because chlorine is the same element, that means they have the same attraction, they have the same electronegativity, so the poles are exactly opposite. It's like two strong men pulling on a tug of war. The flag's still going to stay in the middle. Nobody's winning because they're pulling with equal strength. The electronegativity is the attraction that each nucleus has for that shared pair of electrons. So in the case of the chlorine, when we would talk about this bond, the electron cloud with, I didn't draw it very symmetrical. The electron cloud, as best I got, would be evenly distributed. There wouldn't be electrons more on one side than the other. It's going to be even, an even sharing of electrons. But if I put hydrogen with chlorine, chlorine has a much higher electronegativity than this. So when they're pulling, it's going to be kind of pulling like that and pulling like that in terms of strength. The chlorine's got a much greater pull for the shared pair than the hydrogen does. So when we look at the electron cloud here, the electron cloud is going to be much more around the chlorine than it is around the hydrogen. Well, what's the charge on an electron? Negative. So if you have more negative now around the chlorine is going to be more of a, it's going to have the negative pole, and the hydrogen is going to have the positive pole. But it's not a complete transfer of electrons like an ion, it's just an uneven sharing. And so we use this delta, this partial, meaning it's going to have a partial negative and a partial positive charge. It's due to an uneven sharing of electrons. Okay? So polar bonds result from an uneven sharing of electrons, which causes the shared pair of electrons to hang out, to be the probability of where you're going to find them, more around the more electronegative element. Okay? Now this is a scale. This is a scale from 0 to 4, with this being weak and this as being a strong attraction for the shared pair. Fluorine is the greatest, has the highest, and it's right at 4. And francium is the lowest at 0.7. Now your periodic table, this, oh shoot, I didn't give this back to him. This is Jackson's. Okay, your periodic table has the electronegativities on the back side, in the corner, and the key down at the bottom tells you where it's going to be. It's going to be up in the top left, top right corner is where the electronegativities are going to be. Okay. Now you're not going to have any of these memorized, but if you look in your book, chapter 12. Okay, here is a table of electronegativities. Okay, table of electronegativities. Notice we have the alkali metals are the lowest. Francium's down there at 0.7. Notice the ones up here in purple: nitrogen, oxygen, fluorine, and chlorine. Now, on your periodic table, nitrogen is actually 3.04. Oxygen is given as 3.44. Fluorine is 3.98, and chlorine is 3.16. Now, I don't know why. There's just different methods of measuring those. They're all still really close to the ones in the book are the ones that are in almost every textbook, where there's just more general. But your periodic table gives a little bit more exact ones. Okay. Notice that the top 4 are the most electronegative, meaning that they got the greatest attraction for a shared pair of electrons. We're going to remember that with an acronym, and we're going to just remember phone call. F-O-N-C-O. Phone call. It's a way of remembering that those are my 4 most electronegative elements. if those elements are involved in a bond, they're probably not gonna have an even sharing. They failed kindergarten. They did not learn how to share well. Okay? They have a strong attraction for the shared pair of electrons. I'm gonna leave it here while you guys are copying that. So when we're looking at this here, what happened? Oh, I moved it. Oh well. Okay, I'm just. When we're looking at our scale, we're gonna let the X equal the difference in electronegativity. If the difference in electronegativity between the two atoms that are bonding is less than 0.4, we're gonna call it a nonpolar bond. Okay? This means it's gonna have an even sharing. But if X is between 0.4 and 1.7, we're going to call it a polar covalent bond. Meaning what in terms of electrons? What do I change? What do we say a polar bond is?
Even sharing.
An uneven sharing. But if the difference in electronegativity is greater than 1.7, we're going to call this an ionic bond. And what's the word for ionic with electrons? Transfer. Somebody whispered. So rather than sharing, it is transferred. Now, we can see this on your periodic table. On the back side of the periodic table up at the top, it has a chart with difference in electronegativity versus ionic character. So if you look at this up here at the top, you can see that if the difference in electronegativity down here is 0.4 or less, it's only got like a 4% or less of ionic character. We're going to call it pretty much an even sharing of electrons. The pull is about the same. If we're between 0.4, what happens at 1.7? If the difference in electronegativity is greater than 1.7, what happens? What do you mean? I know that, but why? What happens to my ionic character? What is it at 1.7? 51%. Meaning now it's more ionic in nature than it is covalent in nature. So we say if the difference in electronegativity is greater than 1.7, then it's going to be an ionic type bond, not a covalent bond. Well, when we go back and look, we saw, come over here, we saw that the alkali metals have the lowest electronegativities. The nonmetals over here have the highest electronegativities. Therefore, they're going to have the biggest difference between them. So a metal with a nonmetal gives you what type of bond? An ionic bond, because you got the biggest difference in electronegativity. One is strong enough to completely just take the electrons away from the other one, transfer. But if you have two nonmetals combining, now their electronegativity is going to be much closer. So you're not going to have, one's not going to be strong enough to take it away. They're just going to share, but they don't always share equally. If foam call is present, if a fluorine, oxygen, nitrogen, or chlorine are present, more than likely you're going to have an uneven sharing of the electrons. You're going to have a polar bond. But if one of those isn't present, that means these all have nearly the same, they're all much lower, So you're gonna have a much smaller difference in electronegativities, so it's probably gonna be in more of a nonpolar bond. So we're gonna look for phone call. We're not gonna have to look for exact values. We're not gonna go and do subtractions and try and get my percent, and all that. You would have to know all those values. We're just going to look at if it's a metal and a non-metal, it's ionic. There's gonna be a big difference. If it's two non-metals, if fluorine, oxygen, nitrogen, and chlorine are present, then it's gonna be polar. If it's not present, then it's probably gonna be a non-polar bond. Now, we are running out of time. Don't put away quite yet. Okay, hold on. Okay, but there's a second factor on whether or not the molecule is going to be polar or not. That's going to be based on the shape. And so when we come in tomorrow, we're going to have to look at real quickly how the shape is going to affect it. Okay, we got to get caught up there because then tomorrow, the rest of tomorrow will be a review. But we got to talk about how the shape is going to affect the polarity, and that's going to be the last thing that you're going to be responsible for. And then from that, then we'll review and take the test on Thursday. Okay? All right. Y'all need to start doing that. I put a study guide. Did I put a study guide? Yeah, I did in classroom. I did put one in the classroom. You need to be looking at that. And don't forget, you also need to know the periodic table stuff. That's all pretty much classification. I don't even think it's one to do. I think it's just a know. Well, actually, it is a fill-in thing. But yeah, I don't even think I'm going to collect it. You just need to know how to do it. Okay? All right. Y'all have a great day and go Jags.